So we had a look at Dr. Mike, and he talked about the pigeonhole principle. Well, what we're going to do right now is I'm going to kind of walk you through our first video quiz, okay? So if you have not downloaded Video Quiz 2 yet, if you would please do that. You actually don't have to print it. You can actually just look at Video Quiz 2 on your computer or your phone or your iPad or your tablet, and you can use the screen to answer the questions or to see the questions, and the answers, of course, are all there. And you can just jot them down on scrap paper. And then what I'd like you to do is to text me the answers to this video quiz, please, tonight or whenever you get a chance, and so that I can grade them and put them in the book. So this is your chance to get a good grade on your quiz. And also, I just wanted to say, hopefully you sent me a picture of the fact that you worked on the shaking hands problem, because I'll give you 10 points for having done that, just having attempted it, okay? So just send me what you have, and I will be glad to offer you the 10 points for that as well. So if you have this video quiz so that it is loaded up, you don't actually have to load it up if you don't want to, or print it, because I'm going to show it to you right here. So here's video quiz number 2. We don't have a video quiz 1. I don't give that anymore. So just jot down the answers to these, and I'd like to kind of make you understand why I give you these video quizzes. It's to make you think about what we have discussed very recently in the videos, okay? So here we go. Let's give it a shot. So let me switch over to the very first question. It says you learned in class that there are 2 different ways to show a collection of mathematical objects: by writing a list or by showing or writing a set. Which choice below correctly shows a list, not a set now, but a list of the even, natural, or counting numbers? So please jot down your answer for that. And let's go to the next question. Which properties or points must be included when stating the possible definition of the pigeonhole principle? Okay, now, I'm very wordy a lot of times in these problems, so you have to be very careful not to get lost in all my wordiness. Look at A. If you have more pigeons than holes for the pigeons to fly into, then you know at least 2 pigeons will have to fly into the same hole. Now, if you feel that's correct, hang on, let's look at the other answers. B, if you have more pigeons than holes for the pigeons to fly into, then duplication of the use of a hole, pigeonhole, must occur. Look at C. If you have more pigeons than holes for the pigeons to fly into, then there is no way each pigeon, will have its own unique hole, all of its own, to fly into. Some pigeons will have to share entry holes. Or is the answer D, each of the above statements apply to the pigeonhole principle? So jot down your choice, okay? And let's move to the next question. Which do you think would be an example of a finite set? Remember, that's the opposite of being infinite. Infinite goes on forever. A finite set that is so doggone large that it's impossible really to count all of its elements. The students that would be present in our math class today, if we were meeting on campus, the names of the people who were arrested in Buffalo, New York over the past holiday weekend, the cell phone telephone numbers in use presently in the United States. the auto license plate numbers of all vehicles parked directly behind Rockwell Hall on campus right now? Or would the answer possibly be none of the above? I'll give you a hint. The answer is not none of the above. Okay, jot down your choice to question 3. Let's go to question 4. Let's assume that every student present in a particular classroom today is between the ages of 17 and 30. Now, if they're from 17 to 30 years old, that means if you include 17 and you include 30, that means that spans over 14 years. There are 14 years of different ages in there, okay? There are 25 students in the class. If so, which statement must apply or definitely be true about the members of the class? A, no students present were born in the same year. At least 2 students present were born in the same year. No 2 students present were born in the same month. No students present were born on the same day of the year, like August 23rd. Or E, none of the above conclusions can be drawn. Now remember, think of the pigeonhole principle. There are more students than there are different ages for them to be, right? So think about that when answering this question. Okay, jot your answer down. By the way, usually when I give you these video quizzes, well, not usually, but a lot of times I will give these to you and you will have them just on paper and you'll write the answers down and text them back to me. So, but today I decided to help you a little bit with this quiz since it's our first one. All right, and here's finally question 5. By the way, these are 10-point quizzes. Each question's correct answer is worth 2 points in your pocket. So here we go. Number 5. Again, let's assume there are 25 students attending a class and that every student present in the class today is between the ages of 17 and 30. In other words, their ages span over 14 years. Is it possible that none of the students there were born in the same month of the year? Of the same year, that is. Now think about it for a minute. How many months are there in 14 years? A lot of months, right? If you take 14 years and on a calculator and multiply it times 12 months in a year, you get 168 months exist over 14 years. So is it possible that none of the students in the class were born in the same month of the same year? No for A. There were more people present than birth years. Yes, there are more months available to be born in than there are students present today in class. C, I have no idea. I don't suggest you pick that choice. And D, there's not enough information presented to draw an accurate conclusion. All right, you put down there what you feel the correct answer should be. Now don't forget, you are to send those to me, okay? Now, I'm going to switch screens here. So we're going back to this one, and I have to stop the share on the other screen and share the screen we are about to be on right now. So let me do that so I know that you can see what I'm talking about. So let's move on. Okay. I would like you to bring up the sheet called Group Work number 2. Group work number 2. Either have it on your pad or your computer or whatever. And if you didn't print it, that's okay. But let's solve this problem. It says, estimate the number of golf balls that would fill this box. A golf ball is 1.5 inches in diameter. Show your work. Now, gee, we'll assume these dimensions are the inside of the container, not the outside, the inside of the container. And we'll assume that the golf balls go right next to each other. Let me just give you a quick example of something. They're not going to be in there in a weird way like this, all right? They're going to be right next to each other going across, and then the next row goes across. So they're not going to be jammed in between each other, kind of. They're going to be just lined up in rows exactly the same way. All right. We need to get the volume of this thing, don't we? In golf balls. Now, if we're going to get the volume of this thing in golf balls, and by the way, by doing this sheet together with me today, remember, you get 10 points for having done that. All right? So let's get to work on this, and let's earn yourself another 10 points. Sounds pretty good to me, right? Estimate the number of golf balls that will fill this box. Well, how many golf balls would fit across here? That place where I'm showing that kind of blue thing across there. How many golf balls would fit across there? Well, how many golf balls would there be in a distance of 3 yards? We line them up exactly next to each other. Well, let's see. This is another use of dimensional analysis, folks. If we take 3 yards and we want to convert it to golf balls, all we simply have to do is put down 3 yards. Now, a lot of you are not familiar maybe or remember maybe that there are 36 inches in a yard. But if you remember there's 3 feet in a yard and there's 12 inches in a foot, you can see there would be 36 inches in a yard, right? So let's convert these 3 yards into inches since the diameter of the golf balls is written for us in inches. Okay, so let's do that. Where will yards go so it goes away? On the bottom. For every 1 yard, we have 36 inches. I probably should use IN, but this symbol up here is supposed to mean inches. I'm still not where I want to be. I want to know how many golf balls fit across there. Well, let's see. There is 1.5 inches of golf ball, all right, for each of them, right? So if I want to convert inches to golf balls, I want to get rid of inches. So 1.5 inches would go here. By the way, yards has canceled. Now I'm going to have inches cancel. 1.5 inches equals 1 GB, 1 golf ball. So what is the answer to this? Well, look, folks, if we do this problem, you can see we can multiply the top together, 3 times 36, all right? So I'm grabbing a calculator here. I'm going to do 3 times 36. I got 108, and I'm going to divide that by what's on the bottom, the 1.5. So I hit divided by 1.5, and I hit enter, and I get 72. So over a 3-yard distance like that, there would be 72 golf balls lined up next to each other. Now, this box is actually called a square prism because its base is actually a square, right? It's 3 yards by 3 yards on the bottom, and it doesn't look like a square because it's 3D, but it is a square base on there. So both the width and the length of the figure is 72 golf balls, right? So this is 72 golf balls down here. This is 72 golf balls right here. Now, how many golf balls could I stack on top of each other in a row if it's 5 yards? All right, to do that, what I will do is convert 5 yards into golf balls. Again, it's 36 inches per every 1 yard. For each golf ball, it is 1.5 inches in diameter. So what I will do here is 5 times 36, so I clear it. 5 times 36, I get my answer, and I divide it by 1.5, and I find there would be 120 golf balls stacked on top of each other on each of the golf balls that fill up the bottom. How do I get the number of golf balls in here? Well, do you remember from middle school and high school that the formula you can use to get the volume of a square prism or a rectangular prism is what? Do you remember it? It is V equals LWH, length times width times height. And of course, we found the height of this to be 120 golf balls, right? So it'll be what? The volume is 72 times 72 times 120. All right? So let me see if I can get that for us. 72 times 72 times 120. And I get 62, let's see, 10 to the third, 622,080. Gosh, could that be that big? Yeah, I think so. 60, let me write that down, 622,080 golf balls. Now that is a lot of golf balls, okay? Notice we use the powers of estimation and our common sense and dimensional analysis to help us solve this problem, okay? So that's just a perfect example of some type of problem I will give you on your first major test, which will probably occur maybe this Friday. We'll see if we get that far, okay? All right, let's go on. There are 361,000 babies born in the world every day. Explain why some babies born today will also die on the same day. You may safely assume that no one lives more than 110 years. Okay? Now, I don't want to sound morbid here. We're not talking about the baby dying on the day it was born. We're talking about the baby dying on their birthday. Okay? Well, let's see. How many days are there in 110 years? We need to know that, right? Because we're dealing with 361,000 babies, right? So let's take a look at that. Let's see. If we have 110 years, and we want to convert that to how many days there are, right? I would multiply by 365 days for every 1 year. So let's see, if I do 110 times 365, I get 40,150 days will occur in 110 years. 40,150 days. Can you imagine living to 110 years old? That means you would have lived 40,150 days. Not too bad, right? Pretty good. All right, now, explain why we know some of these babies, when they grow up, are going to die on the same day they were born. Well, I think you can see this is an example of the pigeonhole principle. There are more days than there are babies, right, that have been born. Okay? So there are more days to die on than there are people who are going to be dying, right? True? So because of that, there's got to be some duplication. Now I'm going to tell you how I usually allow you to write this on a test. You can write PHP, baby. PHP means what? Pigeonhole principle. So because of PHP, baby, we know that there are going to be many people that die on the same day. Okay? Could be their birthday, could be any day. I may have misled you a little there, but we know there are more days to die on than there are people to die. So some of them have to die on the same day, whether it be their birthday or not. Okay? You with me? All right, I may have misled you there a little bit. Now, what else do you need to say to me if you're taking a test and you're telling me it's pigeonhole principle? You've got to explain to me that duplication occurs and what the duplication is going to be and why it's going to occur. Well, there are more days to die on than people dying. Remember 3 dots like this in high school? Therefore, duplication of death days must occur. Must occur, okay? So that's a perfect example of a problem that involves the pigeonhole principle, okay? And we're saying why the pigeonhole principle applies, because there are more days than there are people dying. So therefore, duplication has to occur. Okay, let's go on. Now, this is kind of a weird problem, okay? And what this weird problem is saying is this. You are a slob, okay? And you have a roommate. And you don't want to wake up your roommate. But when you do your wash and you wash your socks, okay, you are such a pig that you don't put the same color socks together. You just take all the socks out of the dryer and you yift them in your top drawer of your dresser. Okay? So they're all mixed up. Now, there are 10 pair of socks. 5 of the pair are black. 5 of the pair, I believe, I got to move this to remember if it's blue. I think it's blue. Yes, 5 are blue. Okay? So, they're all mixed up. It's early in the morning. You don't want to turn the lights on in the dark room to wake up your roommate. So how many socks must you pull out of the drawer without looking and being able to see the colors to guarantee that a pair of the socks is one color? How many must you pull out to have 2 good pairs of socks? Each pair is the same color. And finally, how many must you pull out to be certain you have a pair of black socks? Now, a lot of teachers teach this by using the pigeonhole principle. I teach it by using common sense. All right? So let's apply some common sense to this and see if we can make some sense out of it. Notice here, I have the pairs of socks, okay? But I've arranged them so that they look like they're arranged, but in their drawer, they're all mixed up. Okay, so let's go back to the first question. What did it say? How many socks must you pull out to guarantee that you have a pair of socks that is one color? All right, well, let's take a look at that. All right, let's say I pull a black sock out first, okay? And then in my second draw, I happen to pick out this blue sock. Hey, those aren't the same color, right? But what has to happen when you take the next sock out of the drawer? you're either going to have what? 2 black ones, right? Or you're going to have 2 blue ones, right? So what is the answer to this question? The answer to this question is you must draw out 3 socks in order to make sure you have 1 matched pair. All right, let's go back. How many socks must you pull out to have 2 good pairs of socks of the same color? Now, there can be a pair of black ones, a pair of blue ones. That's okay. They can all 4 be black, and they could all 4 be blue. All right? But they got to have 2 pair. Now, let's go and take a look at that. So let's go over here. What if I drew a black sock out first? I could actually draw 4 black socks out in a row, right? And if I did that, I've done it in 4 socks being drawn, right? Well, that's cool. But that's not necessarily going to be the case. That's not going to guarantee that we have 2 pair of socks that are the same color. For example, let's go back. What if instead I drew 3 blue ones in a row? Or excuse me, 3 black ones in a row like I have here. And then I drew a blue one. I still don't have 2 pair of socks the same color, right? Now, what happens on the next draw? If I draw a blue one, I would have 2 matched pair, right? Or if I draw a black one, I would have 2 matched pair. So it appears that I'm going to have to draw 5 socks out of the drawer to absolutely guarantee that I have 2 matched pair. Now wait a minute. What if I had done this? What if I had drawn 2 blue ones and 2 black ones? Well, I would have done it in 4, but that doesn't guarantee it, right? Because instead I could have drawn 3 blue ones and 1 black one, which means I need another sock to have 2 pair that are the same color. If I draw a blue one, I'm all set. And if I draw a black one, I'm all set because I have a pair of blue and a pair of black. So the answer to this question is 5 socks have to be drawn out of the drawer. Now let's go back to the original question. Okay. How many must you pull out of the drawer to be certain you have a pair of black socks? All right, let's go up here. Hey, you know what? It probably would never, ever happen. But is it possible that you could draw all the blue socks out first with never having drawn a black one? It is, right? So if you drew all of these out, okay, if you drew all of these out, okay, you would have drawn out 10 socks so far. And how many more would you have to draw, right, to have what you want? Well, you'd have to draw out 2 more. And now I'd have a pair of black socks. So what's the answer to this question? The answer to this question is that you need to draw out 12 socks if you're in the dark, and you're absolutely guaranteed you'll have 2 black ones. Certainly you probably would have 2 black ones if you didn't draw out all 10, right, of the blue ones first, but you got to cover yourself. I will be asking you this type of question on your first major test on Friday about something similar to this, okay? So I thought we ought to go over that. So make sure you keep this sheet handy so you know that we will probably be going over that material on the test coming up. Okay. Now, if you could save a quarter every 20 minutes, both night and day, how much money would you be able to save? I've got my picture up here in the corner, so I've got to get it out of the way. In 7 years, how much money could I save in 7 years if every 20 minutes, right, I saved a quarter? Don't I have to get 7 years into money? This is another example of a dimensional analysis problem. So I'm going to start out with 7 years, okay? Okay. Now, I got to get 7 years down into minutes, right? So let's see. There are 365 days in a year. Years would cancel. There are 24 hours in a day. I need to go to that next, right? All right. So days is canceled. Now I want to get into minutes. Okay. So let's see. Hours has to go to the bottom, so it goes away, right? Minutes would go on top. 60 minutes in every hour. But now wait a minute. I'm going to save a quarter, 1/4 every 20 minutes. Okay? Every 20 minutes. Well, now this answer would be in minutes, right? But I only want every 20 minutes. So if I put what? 20 minutes down here and 1/4, and by the way, I'm going to put the quarter in terms of a dollar, not in terms of, cents. So 25 cents every 20 minutes. Now, can you see, I don't have to really think too hard about this problem as I put these steps down, because these steps help me make the problem easier, all right? It tells me exactly how to do the problem. That's why I'm so much in favor of dimensional analysis, because it gives us exactly the process we need to do to solve the problem. Okay, now remember I talked about we could do cancellation, okay? So if I take this 20 minutes right here, this 20, and cancel it with the 60, that's 3, and this becomes 1 down here, right? So now all I have to do now is multiply all the top together. Now this calculator's being really weird I've got over here. So I'm going to do the calculation behind me here on another calculator I have. So I'm going to do 7 times 365 times 24 times 3 times 0.25. And the answer I get, are you ready for this? Are you ready for this? You would save $45,990 if you could save a quarter every 20 minutes. Wow, that's pretty cool, right? Pretty cool. Now, let's go on. All right, well, I guess I don't have another problem for us to look at, and I don't have the sheet right near me in front of me, but I think we have finished, okay, everything on group work 2, okay? So now we're going on to talk about material that'll get us ready for video quiz number 3 that's coming up, okay? So let's get into that. Ooh, what's that? Looks like a checkerboard, right? Okay. What I would like you to do is get out or look at the checkerboard. If you printed it, that'd be great, because then you can write on it. Let's take a look at a problem that involves this checkerboard. Okay, now here is the problem I'm going to present to you. I do not have it written out for you. I'm going to explain it to you. It is ancient times, and in these ancient times, we have a king who believes very much in his minister of science. And his minister of science comes running in one day to the king's, if you will, throne room and says to the king, "Hey, king, you know what? You better warn everybody that lives in this country that you rule that it's going to get dark tomorrow afternoon at 3 o'clock, totally pitch black, because there's going to be an eclipse of the sun." Okay? And no one's going to be able to see. Well, the people are going to be frantic, thinking that something is wrong, okay, that they're dying or something, but they're not, because in about 20 minutes it'll come back to a situation where it'll be perfectly daylight again. Okay? So the king says, "Wow, that's a great idea." So he gets all his horsemen and soldiers together, and they can run all over the land that he is over, that he rules, and they tell everybody, the peasants, everybody that's there, that it's going to get dark tomorrow at 3:30 in the afternoon. Do not worry, the sun will come back. And the next day comes, and sure enough, at 3:30, it's pitch black. The sun, the moon moves over the sun, okay, lines up with it, and totally cuts off the daylight. It's totally pitch black, okay? And then, obviously, the sun comes back again when the moon goes by. All right. Well, the king is so thrilled with what this minister of science has done that he says, "Okay, minister of science, I would like to reward you." Oh, minister of science says, "That'd be great. How can I reward you?" The minister of science says, "Well, take out a checkerboard. And on the checkerboard, I would like you to do the following. On the first square of the checkerboard, I would like you to put one piece of gold. And when we're all done with the checkerboard, you're going to give me all the pieces of gold." King says, "That sounds reasonable. Let's do it." Okay? So what I'm going to do here is I'm going to, let me see here. I got to get the right color here so you can see this. Let's see, will green work? I don't know. Let's see. Maybe not. I think yellow works the best. So I'm going to go here, and I'm going to go to the color yellow. All right, so here we go. Let's do what the king started to do. First square, he puts one piece of gold. Now, the minister of science said to him, "Hey, on the next square, double what you had on the first square." So he does. 2 pieces of gold. Okay? We go to the third square. You double what was on the second square. We're up to 4 pieces of gold. Double again. 8, 16, 32, 64, 128. Wow. By the time he finishes the first row, he's got 128 pieces of gold on the last square of the first row. 256, 512, 1024. Now, to complete the story, I wonder why the king put the minister of science to death. He killed him. Well, it should be somewhat obvious that the number that's going to be on the last square down there is going to be absolutely huge. And if you add up all of those pieces of gold that are on this whole checkerboard, it's going to be massive. And I'm wondering, is there a way we can use a shortcut notation to represent each of these squares, the number of pieces of gold on it? Okay, well, let's see. You remember powers of 2, right? What is 2 to the first power? Isn't it 2? What's 2 to the second power? Isn't it 4? What's 2 to the third power? It's 2 times 2 times 2, or 8. These numbers all appear to be powers of 2, don't they? What's the first square? It's a 1. Actually, if you recall, any number raised to the 0 power has a value of 1 in mathematics, right? So this is actually 2 to the 0 power right here. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, and 2 to the seventh, and so forth. Now let me ask you something. What's the power going to be on the very last square down here? What's going to be the power there? Well, most people think it's going to be 64 because there are 64 squares here. But notice the first power was a 0. And when we completed the first row, we were only to 7. And the next row would end at 15. And the next one would end at 23. So it turns out the last square will have 2 to the 63rd power pieces of gold on it. Holy crap, that's a lot of gold. That is a whole lot of gold. This type of growth is referred to, because we're dealing with exponents here, this type of growth is called exponential growth. And you can see these are all powers of 2. All right, and you can see the numbers grow wildly as we get higher and higher. If you do 2 to the 63rd power on your calculator, it'll fill it up so large that you can't even imagine that number, okay? It'll print it in scientific notation, actually, and we're going to talk a little bit about that in a few minutes. But, all right. Now, there's a couple other neat things I'd like to show you about this checkerboard here, okay? First of all, I want you to look at this square right here that has the 8 in it, okay? Now, if you look at the 8, add the squares together prior to that, what the numbers are in there. What's 1 plus 2 plus 4? It's 7, right? 8 is 1 more than the 3 squares in front of it. Isn't that kind of cool? All right, let's look at 64. The square 60 that has 64 in it. Guess what? If I add 32, 16, 8, 4, 2, and 1, I will get what? 63. Okay? So the power is, okay, the square's value, excuse me, is equal to, right? It's equal to 1 less, the 64 in other words, is 1 more, excuse me, than all the other squares put in front of it. Okay? Now, what's that mean for the last square down here? 2 to the 63rd power. So in other words, if I did another square, which I don't have, and I did 2 to the 64th power, and I subtracted 1 from it, I would have the sum of all the other squares amounts of gold pieces added together. One huge mama number, right? Crazy, crazy. So again, this is exponential growth. Now, with that in mind, okay, why don't you get out your phone or your calculator and let's evaluate these various figures, okay? Would you please do on your calculator 2 to the 13th power, okay? 2 to the 13th power. My calculator over here is dying here. The one I want to use, this one's not working right at all. So let me see if I can find another calculator handy here. Don't seem to have one. But 2 to the 13th power would be 2 times itself 13 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 8,192, I believe, is the answer to that. So that's 8,192. All right. Now on your calculator, if you're having trouble with this, okay, I'm going to write down these questions: 2 to the 13th, 5 to the 7th, 3 to the 4th, and 12 to the 17th power. And what I'm going to do is I'm going to bring a calculator up on the screen. So what I have to do is go in here and find my calculator. And I have found it. And I'm going to have to share that screen with you. Give me a second to load it. It's loading up. Okay. Has to make sure that I have registered the software, so it doesn't want me to cheat. Okay. Still validating the software. And I'm going to go to large screen. Now I'm going to go back here and I'm going to stop the share we had. Okay, I'm going to share the screen with my calculator, which is right here. So you all should see the calculator right now. Now, the TI-30XS, which you see in front of you, is a very nice calculator. If you have a TI-30, I can't think of the TI number that you use, TI-64, I think it is, I can't remember, that you used in high school. I think it was an 84, actually. If you have one of those, you're in good shape because you can use it in this course, obviously, okay? So let's see. What happens if I do 2 to the 13th on here? To do it on this calculator, remember, I simply do 2, and then I hit this little caret key right over here. See it right there? Caret, and I hit 13, which is the exponent, and then I hit enter, and I get my 8192 that I already told you about a couple seconds ago, right? Okay. Now, if you're using your phone to do this, the key you have to use is the Y to the X key. What you do is you enter your bottom number 2, you hit the Y to the X key, all right, and then you enter the 13 and then hit enter and it'll give you the 8192. So the exponents work a little differently on a regular phone rather than they do on a scientific calculator like we have here. Also remember, on your phone, you have to actually take your phone and turn it sideways. And if you turn your phone sideways, it becomes a scientific calculator. So if you can find the calculator on your phone, you're able to do that. Now, if you have a calculator handy, obviously you're in good shape and ready to go here. All right, next I'm going to do the next problem on your sheet there, okay? And the next problem on the sheet, which I think was the back of group work number 2, right, was to do, excuse me, on the back of the checkerboard. On the back of your checkerboard, it wasn't the back, it was the second sheet. It says checkerboard back, and the checkerboard back has these problems on it in case you're having trouble finding these problems. All right, I'm going to do 5 to the 7th power. So I'm going to do 5 to the little caret key, 7, enter, and I got 78,125. Okay. Now I think I'm only can use 2 lines on here, so I'm going to clear this. Next I'm going to do the 3 to the 4th power. So 3 caret 4, enter. I get 81. Of course, that's not too hard. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So that shouldn't be too difficult to see. But the last one, 12 to the 17th power, is a bit of a bear. 12 caret 17. When I do that, I get this big mother number. What does that number mean? Well, in case you've forgotten from high school, the decimal point is put after the first digit, 2, and you've got 2.218611111, all right? And then you've got, I'm not sure what you've got there, but you have, oh yeah, times 10 to the 18th power. The time sign there is kind of weird. All right, so it's times 10 to the 18th power. Do you understand that this number is written in scientific notation? When you write a number in scientific notation, like we did here, right? What it means is, if you recall, that the decimal point behind that first 2 should really be 18 moves to the right. Now, how many digits are there showing up on here? After the decimal point, there are 1, 2, 3, 4, 5, 6, 7, 8 digits showing up. So you would have to put 10 zeros after those 8 digits to give an approximation of the number. Now, some calculators don't print times 10 to the 18th. Some calculators print E18. If they print E18, it means 10 to the 18th power. Okay, any question on that? I think this is a review of stuff you've seen in high school, so I'm not too concerned about you knowing that information. So I'm sure you are aware of it. All right, I'm going to close this out, and what's going to happen is that I'm going back to the sheet that we had, so I have to go back to that. So give me a second to get back to the sheet that I was on, which is this one, which is the back of the checkerboard. I'm going to share again. All right. Now, let me ask you a question. You've all folded paper before, right? How many layers of paper do you have if you take a normal sheet of paper and fold it in half? Well, you can see right here, I have a sheet of paper here, and I have folded it in half. Notice it has 2 layers, right? What if I fold this sheet of paper again? What will happen? Well, when I fold the sheet of paper again, how many layers do I have? Notice there are 1, 2, 3, 4 layers, right? If I fold it again, okay, and I count the layers, there will be 8 of them. Does this sound familiar at all? Well, if we go back a couple of screens here, do you remember our checkerboard? First piece of paper had 1 thickness. When I folded it once, it had 2 thicknesses. When I folded it twice, it had 4 thicknesses up here. You can see it right here on the checkerboard, right? 16 would be the next fold. 32 would be the next fold. What's the power of 2 up there? The power of 2 is the number of times you folded the sheet of paper, right? In other words, if you fold a piece of paper 6 times, you'll have 64 layers of thickness. 7 times, you'll have 128. 8 times, you'll have 256 layers of paper. It's like stacking, 256 pieces of paper on top of each other, right? Okay? You get the idea, right? Now, let's go back to this crazy question I've asked here. How many times would you have to fold a tremendously huge piece of paper, if you could do it, to have surpassed the height of 1 mile? What? 1 mile. Now, first, I forgot a question. How many pieces of paper would be required to produce a stack of paper? Oh, it's the same question, right? They would produce a stack of paper that's a mile high. Okay, the second part is asking the same thing. Okay, sorry about that. So, let's see. Well, the first thing we got to agree upon here is how many pieces of paper there are. Okay, for some reason I've lost my use of using my smartboard here, so let me, I can get it back. It's not helping me out much here. There we go. Okay, let's see. Now, First thing we got to decide is, you know what? How thick is a stack of paper in terms of measurement? Okay? That's kind of weird, right? Well, what I did when I first started to teach this class is I went home and I got out some reams of paper. Now, let me grab a ream of paper real quick for you here so you know what I'm talking about. If you remember, a ream of paper, right? Okay, having trouble grabbing it here. Hold on. A ream of paper comes wrapped up like this, right? Comes wrapped up like this, like a present, right? How many sheets of paper are in there? Do you know that? Well, it turns out a ream of paper that you buy paper in boxes, and the boxes come with 10 reams in them, okay? So when you buy this paper, okay, how thick is a ream of paper? So what I did is I came home and I decided to measure the thickness of a ream of paper. And when I did, I found out it's almost exactly 2 inches thick. So I want you to always remember that a ream of paper, all right, is 2 inches thick. Now, wait a minute. A half a ream would be 250 sheets, right? So 250 sheets would be what? 1 inch. So you can use either equivalent. Now, if I want to know how many pieces of paper I could stack on top of each other, normal copy paper, to reach the height of 1 mile, right? Whoa, baby. How much do I need? Well, let's see. We got to figure out how to do that. And I wonder if dimensional analysis will help us, right? Wonder if dimensional analysis will help us on that. All right? So we need to get 1 mile into sheets of paper. So what I'm going to do is I'm going to write down here 1 mile, okay? And I want to make it become sheets of paper thick to get that height, okay? So let's see, how will I do that? Well, I'm going to have to change it down into inches, I would guess, right? And once I know how many inches 1 mile is, I can make it sheets of paper, can't I? So let's do this. Let's convert to 5,280 feet per every 1 mile. Okay. Miles will cancel. I need to get feet down into inches. So I've got to do what? Feet goes to the bottom. For every 1 foot, there are 12 inches, right? Okay, now what? Well, let's see. Once this answer's in inches, how do I get it into sheets of paper thick? Well, the way I do that is I realize that for every 250 sheets of paper, it's 1 inch thick, right? So I'm going to put 250 sheets. SHTS doesn't stand for the bad word. It stands for sheets. All right, so 250 sheets per every 1 inch. Now, if I multiply that out, right, I will determine the number of sheets of paper that I need to stack on top of each other to have the thickness of 1 mile. Now, since this calculator is giving me trouble over here, I'm doing it back here. So it's going to be 5,280 times 12 times 250 equals 15,840,000 sheets of paper. That's a 5 there. 15 million. Okay? Now let me erase that and make the 15 look a little better. Okay, so 15,840,000 sheets of paper. Now I wonder if we can answer the next question. How many times would I have to fold a tremendously huge piece of paper, if I could really do it, so it would surpass that height of 1 mile? If I actually could fold a sheet of paper and keep folding it in half and folding it in half, folding it in half and folding it in half, how many times would I have to fold it to beat 15,840,000 sheets of thickness? You know what? That's kind of a crazy question, but let me write this down. Every time you do a sheet of paper and fold it in half, you're doing a power of 2. Remember, if it's 2 to the 3rd, you fold it 3 times. If it's 2 to the 8th, you fold it 8 times. I want to know how many times I would have to fold a piece of paper, because every time I do it, I double the thickness, just like the checkerboard worked, right? Will give me a number that is either greater than or equal to 15,840,000. Now, let me just say this. We could solve this by doing a logarithmic equation, but we haven't done logarithmic equations in a long time. So I'm not doing it by logarithmic equations, okay? What I'm going to do instead is T&E, baby. Trial and error. T&E. And by trial and error, I should be able to get pretty close to this answer fairly quickly. What does that mean? What that means is I just start taking powers of 2, and I do the powers of 2 until I beat or equal 15,840 sheets. Okay? So let me get the calculator back up here again. Okay, I'm going to have to share the screen with you again. Take a second for it to load up. Sorry about this delay for you. All right, so I'm going to stop the share, and I'm going to go back to a new share with the calculator. All right, and here we go. I want to do, let's try 2 to the 10th power. Let's see what that gives us. If we do 2 caret 10, what do we get? Ooh, I want to show what the answer is there. 1,024 sheets. I need 15,840,000 sheets. So my number is going to be a heck of a lot bigger than that, right? So if I do these powers of 10, or excuse me, powers of 2, and I can come up with a number that just beats 15,840,000, I know the folded piece of paper, which is impossible to do, but if I could do it, would be the height of 1 mile. All right, let's try 2 to the 20th and see where that puts us. So if we do 2 caret 20, that's 1,048,000. Now remember, we're doubling each time. So if we double that, it'd be 2 million. Double that, it would be roughly 4 or 5 million. So we're getting closer, but we need to be at 15 million. All right, so let's try 25. All right, so let me clear this. If I do 2 caret 25, enter, I get, it looks like, what? Looks like I get, it looks like I have 33 million there, right? So that's a little too big, right? Because I want 15,840,000, right? So that's too large. It's about twice as big as it needs to be. So let's try 2 to the 24th. So let's do 2 caret 24, enter. Ooh, 16,777,216. Now that is bigger than 15,840,000. So if you could fold a sheet of paper 24 times, right? you would surpass the height of 1 mile in thickness. There ain't no way we can do it. But we have to think of it in our mind's eye, it's called. Okay? All right. Let me unshare this screen. All right. Let me go back to the other screen we were working on, which was this one. All right. And let's go on. All right. So we have already answered these questions. Now, we're going to try another video quiz. But this time, I'm going to let you attempt to do it, all right, and just jot the answers down. So I'm not going to go through the questions with you, all right? So I'm going to stop this video right now, okay? And what you're going to do is attempt a video quiz that discusses the questions we had. Now, maybe I'm lying here a little bit, because maybe I would like to discuss one of the problems on there with you. So I'm going to have to reshare the screen, all right? I'm going to go to this video quiz. All right, I'm going to stop the share. All right, I'm going to reshare. We're going to go to the video quiz. I guess I've kind of changed my mind. I'm going to kind of do this video quiz with you. Okay, so if you'd like to, you can get the video quiz up on your screen if you want, or you can look at the screen you have in front of you right now. And we can answer these questions. Okay. Remember, you're to jot these answers down and turn them into me for a grade out of 10 points. All right, if you're using a calculator, and an answer you just computed comes out 1.099951168E12 or 1.099511628 times 10 to the 12th, then you can assume that your answer on the display is close to or is approximately equal to which of these values. Do you remember what the 10 to the 12th tells you? Hint, hint, hint. Doesn't it tell you something about moving the decimal point? So which of these answers correctly moves the decimal point to where it should be to approximate the final answer that would be to this problem? Okay, let's go on. Use your calculator or your phone to determine, I believe it's 2 to the 30th. 2 to the 30th power, okay? Two to the 30th power. Let me give you a hint in case you've forgotten. It's 2 caret 30, right? Or 2 y to the x 30. Now I think probably you have your answer now, so I'm going to move on. Use your calculator or phone to determine which statement here is false. One of those statements is definitely wrong. They're not all true. So pick the value that's wrong. I'll give you a little time to do that. I suggest you work both sides out of those sentences in B and C, and also in D, make sure they're right. I believe one of them is definitely wrong, okay? Now, if you need to, you can come back to this problem when I finish this video. So I'm going to go on. Hopefully you have found which one is incorrect. If you fold a large piece of paper in half 6 times, how many layers of paper, same as sheets of thickness, will you have? How did we do that? We took powers of something, didn't we? Hint, hint, hint. Okay, and last but not least, I want you to think a little bit. Look at the pattern of the numbers found in the squares of this little board. Use your calculator phone to determine the value that should be placed in the last square that I pointed to below. Its value should be what? What are these numbers powers of? They're certainly not powers of 2. Hint, hint, they're powers of another number. So figure out what powers of that other number they are, and then figure out what the power would be you would need for that last square and do it out on your calculator. Now, of course, if you need more time, you can look at your sheet, assuming you printed it, and you can see what the questions were on the quiz without going back to look at the video, but at this point, you're in pretty good shape. Okay, so let me stop the share here, and let me just say that I'm going to end this video because it's kind of long, all right, and we'll be starting up another video shortly. I would like to say that I am going to probably assign a video for you to watch at home by another professor at Buff State tonight to kind of review a little bit of what we've talked about today. So, all right, so but I will be coming back to do more for this particular class, particularly if you're in summer school. So get ready, I'll be back shortly, and we'll talk to you soon.